Welcome to the webinar, Drowning in Alarm Floods. Learn how automatic alarm flood suppression can help. In terms of audio, you are all muted. You're welcome to post questions through the interface on the right-hand side, and we'll, at the end of the presentation, if we have time, we'll go through the questions that have been submitted. And if we don't have time to go through them, I'll address them via document or email afterwards and send that. That'll get sent to everyone. So everyone will get a copy of the questions and the answers. So a little bit about myself. I'm Todd Stauffer, Director of Alarm Management here at exida. Also product manager for a tool that we have called SILAlarm, which is an alarm rationalization tool. I've been heavily involved in alarm management and the development of the standards related to alarm management for almost 20 years now. Been involved with the ISA 18.2 committee that developed the ISA 18.2 standards since early 2000s. Been a voting member since 2005. Was also the co-chair for a couple of technical reports that were created after the standard was produced. And then my current role is as the co-chair for a new standard on safety controls, safety alarms, and safety interlocks called ISA 8491.03. And a little bit about exida. We were founded in 2000 with a vision to make the world a safer place. And when I say the world, I mean process plants mostly. Two gentlemen that worked in the functional safety area thought that they could make a bigger difference in the world, and it was needed, by founding their own company. So that was how exida started. We have our basis, our core foundation is in functional safety and that expertise in that discipline. And about 10 years ago, they realized that safety needed to be expanded to include alarm management and cybersecurity. So that's where those parts of the business came from. We are a leader in the certification of people and devices for safety systems. So if you've ever put together a safety instrumented system with SIL capable or SIL rated equipment, chances are that exida did the assessment to give it the SIL rating. We've done more SIL assessments than any other company. We also have a program for personnel certification, which is a requirement of the functional safety standard. And then last but not least, I just wanted to mention that we have a suite of software for safety instrumented system design. The flagship product, and the name of the suite is called Excellentia. It contains a number of products within it, including the SILAlarm alarm rationalization tool, which we will talk about a little bit today. In terms of the agenda, we're going to look at alarm floods. So what is an alarm flood, and what does it mean when it happens? What does it do to the operator? How does it impact the operator? What can happen? We'll also look at, if you have floods, how do you recognize it? How do you quantify it, measure it, determine what's happened, and then figure out how to fix it? And we'll look at the information and the requirements that are provided in the various standards and guidelines that exist. We'll talk about how alarm rationalization figures into minimizing alarm floods. We'll look at the different types of architectures for implementation, whether it's in the controller itself or on a supervisory computer. And then we'll also look at an actual example, Compressor Trip application, where the compressor trips and you end up with a flood of alarms. We'll look at some examples of how that could be implemented within different control systems, including Emerson DeltaV, Siemens PCS 7, Rockwell PlantPAx, and Yokogawa's Centum platform. So let's start with the definition of what an alarm flood is, or a concept about what an alarm flood is. So a question: is the alarm flood a condition during which the alarm rate is greater than the operator can effectively manage? Is it when the operator gets more than 10 alarms in 10 minutes? Is it a situation that is usually triggered by a single event, such as a plant upset? Or is it one of the most complex alarm management problems to solve? The answer is all of the above. According to the ISA 18.2 standard and the AMUA 191 guideline, an alarm flood is when the operator gets more than 10 alarms in 10 minutes. Now, how do we know when you are actually being the victim of alarm floods and when it's actually happening to your operators? You would notice it because what they'll be doing is furiously acknowledging the alarms or banging on the silence the horn button to be able to concentrate and process what's happening. So you'll end up with a lot of alarms that are coming in that the operator needs to get through as quickly as possible. And in a lot of cases, they are just acknowledging the alarm without really understanding what it's for and what it means. And part of the challenge that they face in that situation is they need to make a quick judgment call about whether the alarm is important, and if it is, what do they do about it? Some of the alarms often are not useful in that case. After a piece of equipment trips, there are a certain set of alarms that you would expect to get. Those are the ones that are not very useful at that point in time, but the operator's got to sort through all of that stuff and try and make sense of it. And that's why alarm floods can be so challenging. So they typically occur during the most stressful times: startup, shutdown, initiation of upsets, and that leads to, significant additional stress on the operator. It can overwhelm them. The sheer number of alarms can overwhelm them, and the stress that's caused of that challenge and of that happening can make it more difficult for the operator to respond effectively. And if we look at this layer protection schematic with different barriers in place to prevent the hazard from escalating, one of the very first ones is in yellow, the alarm and operator response to the alarm. Well, we need that to work. We're counting on that to work with a pretty high reliability for safety purposes. For a typical alarm that one might take credit for in a basic process control system, we would assume a risk reduction level of 10, which means a probability of success of 90% or a probability of failure of 10%. So that's the case for a nominal alarm that we're taking credit for. But look at, in this table here, how the operator's performance, meaning how likely they are to fail, changes when they are put under stress. They go from a less than 1% probability of failure to potentially 50 to 100% probability of failure. So that would mean that this alarm, this layer of protection that we're counting on to prevent the escalation of the hazard is very likely to fail if the operator is being flooded by alarms. So that's one of the serious ramifications of alarm floods. And this was emphasized or came to light in an incident that occurred in 1994 in the UK at the Milford Haven Refinery. The refinery was hit by lightning during the summer, and that started some fires within the equipment of the plant. They shut down most of the operating units, but kept the cat cracker running. And as they were trying to keep it up and running, some of the vessels overflowed. Relief valves went off multiple times, relieved to a knockout drum that became more full of liquid than it was designed for, and that resulted in a rupture of an elbow and a discharge of hydrocarbons that then exploded and caused more fires. And when they investigated to find out what had happened, there were multiple problems, including poor HMI design and some issues with that. But one of the things that they found was there was actually an alarm that said high level in the knockout drum. So the alarm was presented to the operator to tell them that there was something critically wrong and needed their response. The problem was it was one alarm in 275 coming in a period of 11 minutes. That's like a new alarm every 2 to 3 seconds. If you can just imagine that, put yourself in the shoes of the operator, you can see why that was so challenging. So the HSE in the UK did a very thorough investigation. There were reports that were published with lessons learned, and specific research was then gone into collecting best practices for alarm management, which we'll talk about in a second. But some key takeaways from their investigation. Alarms should be limited in number to that which an operator can effectively manage or monitor. So we can't just overload the operator with alarms during a flood and expect them to be able to respond correctly. Second key thing was safety critical alarms, like the high level and that knockout drum, need to be distinguishable from other operational alarms. What happened in the Milford Haven incident was alarms were all set to the same priority. So every one of those 275 alarms had the same priority. So it was very extra difficult for the operator to notice that critical knockout drum high level because it didn't stand out from the other alarms. So key takeaways from that incident that we carry forward in alarm management practices. So as a result of that incident, as I mentioned, the UK launched research and codifying of best practices, and that came into publication with the release of the EMUA 191 guideline, which first came out in 1999. Excuse me. So it was a collection of best practices for alarm management, and it was the best document or best body of knowledge related to alarm management until the ISA 18.2 standard came out in 2009. That's a true standard with requirements and recommendations related to what owners and end users and integrators need to do. Now that was updated in 2016, and it was actually used as the basis to create an international standard called IEC 62682. So those standards now exist to drive alarm management practices. For ISA 18.2, after the standard first came out in 2009, the committee turned their focus to creating technical reports, which went into more detail about how to implement the requirements that exist in the standard. And there's one technical report in particular that I wanted to highlight. It's technical report number 4, which is on advanced alarming. So it covers some of the suppression and alarm flood scenarios that we're going to talk about today. First, let's back up to some basics of what an alarm is, according to the definition of an alarm in those standards. Alarm is supposed to be an audible and or visual means of indicating to the operator, and I underline the word operator because they are the target audience of the system. If the information is not understandable and actionable by the operator, then it doesn't belong in the alarm system. Second point is that the alarm needs to indicate an equipment malfunction, process deviation, or abnormal condition, meaning that something is wrong, something unexpected has happened. And last but not least, it requires a timely response other than acknowledging the alarm. We're talking about opening a valve, turning on a backup pump. So this is the criteria for what makes for a valid alarm. The process of alarm rationalization then is reviewing the alarms that exist in your current system or the alarms that you are proposing to put in and making sure that they meet this definition of an alarm. And this is important because we're going to talk about whether rationalization occurs before we think about doing suppression or whether it occurs at the same time. And you'll see what the recommendation is. Now, one of the reasons why folks have alarm overloads during steady state operations is because they are using the alarm system to notify the operator of everything, even if it's not truly an alarm. So part of the way to clean up the alarm system via rationalization is to eliminate those points that don't meet the definition of an alarm and to recategorize some of them as this alternate form of notification that they might truly be, and then get that out of the alarm summary display. Some of the other key design principles that we will leverage and talk about: making sure that every alarm that's presented to the operator is useful, relevant, and unique. So we're going to talk about doing alarm rationalization actually first to eliminate nuisance alarms, get rid of alarms that don't belong. And then part of what happens during alarm floods is you get alarms that are useful unto themselves, that do serve a purpose. But when that particular event occurs, the alarm is no longer useful or relevant to the operator. So rather than present it to them, rather than give them misleading or useless information, we want to come up with a better way. Present them only the information that they need to know. And then, of course, we also need to design the system so operators are not getting more alarms than they can respond to. And that may mean that some of the alarms are hidden from the operators, those that they don't need to know about or don't need to see, and we only present to them those that make a difference at that point in time, those that help them understand what has happened and help them understand what they need to do. And that's essentially what we will look to do. So to help understand the impact of alarm floods, let's look at the response model for operators responding to an alarm. The first step is they need to detect that the alarm is present. And this can be very challenging if you have a lot of nuisance alarms, if your HMI screen has a lot of flashy colors, and in the middle of an alarm flood. As we heard with the Milford Haven situation, you have alarms kind of just scrolling by on your alarm summary display. It's pretty hard to pick one out as it's continuing to move by and try and understand and figure out what's going on. So alarm floods can impact the operator's ability to even detect a particular alarm is there. But once they do that, then they need to be able to diagnose what the problem is and take the appropriate corrective action. Now, if the operator is getting alarm floods, that will make it difficult for them to detect the alarm, or it will delay their actual detection and processing of it. Now, we talked about how some of the alarms are probably not useful. Well, during the diagnose step, the operator is forced to go through all of those alarms and figure out which ones are relevant to them at that point in time, and then take the correct response. And you can imagine that under stress, that's going to be a difficult proposition, and it's very likely to lead to mistakes. And that shows itself by the operators either not responding in time or not responding correctly. But what really initiated the incorrect response was the alarm floods making it difficult to detect or to diagnose and understand what the situation really is. So it impacts their situation awareness and damages it, hurts it. This also shows a way to think about how many alarms operators can respond to in steady state. And that recommendation and that KPI in the standards is 1 to 2 alarms per 10 minutes. When we get up to 10 alarms in 10 minutes, that's when we call it an alarm flood. But as I mentioned, if you're getting alarm floods, that's going to impact and hurt the operator's situation awareness, because They don't know necessarily which alarms to trust. They need to think about whether the alarm is relevant and meaningful at the time. If they focus on the wrong alarms as being meaningful, it could lead them to misdiagnose and to have a faulty mental model so that their projection of what is happening and what they need to do would be incorrect. So alarm floods can significantly impact the operator's situation awareness and understanding of what is happening in the process. So turning again to the ISA 18.2 standard and the IEC standard, we see that there are some metrics provided, some recommendation performance levels to evaluate or to measure and evaluate yourself against. The recommended steady state alarm rate, as I mentioned, is 1 to 2 alarms per 10 minutes. For alarm floods, we call that any time the operator gets more than 10 alarms in 10 minutes. It's very likely going to be impossible to prevent that from occurring. So what we want to do is minimize the intensity of floods and minimize the duration of floods. So if we look at the duration of alarm floods, we want to try and keep that below 1% of the time. From an operational point of view, that's about 8 hours in a month. So that's one way that we want to benchmark ourselves. This is an example of some actual studies that were done by Emerson of actual performance measurements of how many alarms a system was getting in steady state alarms per 10 minutes, so ranging from up to 1 to 9. And then the y-axis is the maximum number of alarms that they were getting during an alarm flood. And what's interesting here, there's a couple of things that are interesting. You can see that the target, according to the metrics we just looked at, is this little tiny box down here in the lower left-hand corner. And you can see that most of the data points are outside of that box, although many aren't too far away, so that's kind of encouraging. But the other thing I wanted to call your attention to is there doesn't really seem to be a pattern. There are a lot of data points that kind of hug the x-axis here, which means you have systems where there's an alarm overload occurring in steady state, but there's not a real significant alarm flood problem. In other words, the maximum number of alarms during the flood is not that high, is relatively low. So you have that data case, and then you have a lot of data points where they're hugging the y-axis, which means that their steady state alarm rate is fine, but they're still getting some whopper alarm floods. And this is a reason why when people look at alarm measurements, the most common metric to look at is this: how many alarms do you get on average per 10 minutes? But it can't just stop there. That is one metric that helps you evaluate. You can see here that we have some scenarios, look at these data points, for example, where the average number of alarms is really low, but they have a significant alarm flood problem. So if the people that worked at this plant said, well, our average alarm rate is good, so we don't need to do anything more for alarm management, we're in great shape. Well, they would be wrong, because they have some significant challenging alarm floods occurring, and it could be during one of these alarm flood periods where the operator misses a critical alarm and they have a unplanned shutdown or some other incident. So even though their steady state alarm rate was okay, alarm floods were taking them down. So the takeaway is that the elimination of nuisance alarms and reduction of steady state alarm overload is a different problem, different dynamics than elimination of alarm floods. They are relatively independent problems. And what we're going to talk about in terms of how to solve the alarm flood problem is a technique called suppression. There are 3 different types of suppression defined in the standards. The first is called design suppression. That's what we're going to focus on in this webinar. And that is essentially smart alarming to create logic within the control system that detects the changes in states and values of the process and automatically suppresses the alarms that should be suppressed at that point in time, those that are not relevant to the operator. So that's called design suppression. There's also a form called alarm shelving, which is a temporary suppression by the operator, like for nuisance and chattering alarms. And the third type of suppression is called out of service, which is an indefinite suppression, typically to allow maintenance to be performed on the hardware and the alarms. Now, just to shout out to the last webinar that we did, which was on alarm shelving. So if you're interested in that topic and have not seen that, I encourage you to go to our website and check it out. As well as we published an ebook about alarm shelving, which documents a lot about the theory, what it's for, what are the requirements of what you need to provide. And it also does an overview of how alarm shelving is implemented in several control systems, similar to what we're going to talk about today, only we're looking at design suppression. Now, if we were to implement an alarm management program, we would have our alarm philosophy done, and then we would do alarm rationalization. And you should do alarm rationalization thoroughly first before you jump into doing alarm suppression. You can see how that's represented here. It is very possible, although not probable, that your rationalization would be good enough and successful enough to eliminate the need to do alarm flood suppression. But assuming that that's not the case, what probably needs to happen in terms of a timing process is that you do a thorough rationalization of the system, you implement those results, and then you measure and watch your performance. And then based on what you see, that's when you decide or make the decision about whether you need to implement alarm flood suppression. And part of the benefit of doing rationalization first is it reduces the number of alarms that you need to think about in terms of suppression. If you do suppression or think about designing suppression at the same time as rationalization, you're worrying about a lot of alarms that you don't know whether they're truly alarms or not yet because you haven't completed the rationalization process. So that's one of the reasons why, in my personal opinion, it makes sense to focus on doing a thorough rationalization first and then coming back and doing alarm flood suppression separately as a follow-on activity, not doing them together. So now let's look at how we would actually resolve alarm floods or fix them. What could we do? How could we implement something? And we'll look at an example of a DeltaV control system. So as I mentioned, the first step really should be to perform and complete alarm rationalization so that you've eliminated your nuisance alarms and you're down to the smallest number of alarms that you need. Then you can measure alarm performance and identify which alarms are being initiated during floods, potentially what is the cause of it. And in a DeltaV system, you could perform those roles with the DeltaV Analyze software or the Mosaic tool. And then once that's done, you've identified some of the alarms that potentially need to be suppressed. Now you can design how you want the suppression to work. You can design that within the SILAlarm alarm rationalization tool. So it's already got record of the alarms that you've rationalized, what the priorities are. And now you can take it further and say, okay, we want to define an alarm flood suppression group, and then we want to implement that within the control system. So there's a way to export and import it so that it automatically creates the control logic for the alarm flood suppression running in the DeltaV controllers, along with the control modules that it needs to suppress. And then associated with that is HMI configuration, including faceplates for the operator to understand the status displays. So looking at the pieces of that solution, DeltaV Analyze will help you identify alarm floods and look at which alarms occurred to kind of create patterns and understanding. Mosaic also helps you understand what's happening, what's triggering alarm floods, gives you a different presentation way to look at alarm floods. We'll talk about using some predefined control modules in the Emerson DeltaV library, in this case for alarm flood suppression, that were created in conjunction or by partnering between exida and Emerson, which allows you to define or essentially configure them through the SILAlarm tool in a group, and then push that information into DeltaV using the bulk edit tool to enable that logic to run inside the controller. And then those link to faceplates, pre-configured faceplates, that display the information about which alarms are going to be suppressed or which are suppressed and the initiating conditions. So to frame the problem, we need some tools to help us measure and understand what's happening. DeltaV Analyze can do that, showing us the alarms that are part of a particular flood, how long the floods last for, and we want to do significant analysis of so that we can understand the characteristics of the flood. How long does it last for? What's the peak number of alarms? Those kind of things. So if we need to pick a scenario for us to attack, we can use this kind of a performance measurement to help us figure out what should be fixed first. Again, the Mosaic tool, as I mentioned, is a different way to present alarms, either historically or as they're occurring. What you'll find is in the midst of an alarm flood, oftentimes the standard traditional alarm summary display is not very helpful. If what the operator is seeing is alarms, new alarms scrolling by one every couple of seconds, then that's not a very useful, helpful interface. Mosaic provides the alarm information in a different way. You can see the alarms are stacked here, showing which alarms occurred when. These are 10-second slices. So you can get a better feeling for the sequencing between them. It also shows cross-reference to operator actions that were taken at the time. So in terms of defining and understanding causality and what actions were taken, it's a really good tool for doing that. So now let's apply that to a common scenario of a compressor that trips unexpectedly. And as it is spinning down, it creates a whole bunch of alarms that are expected and are not useful and actually get in the way of helping the operator to figure out what's happened and get the system back up and running. So we want to figure out how to deal with that. We'll divide that into two main steps. The first step is the definition of call it a state detection algorithm. So how do we detect when the compressor is tripped? What conditions can we look at? And we'll look at those conditions and create either conditions that must be met, kind of initiators, if you want to call it that, and then some that you'll look at in terms of a voting scheme, perhaps, where you're looking for 2 of 3 or 2 of 4 conditions to be satisfied. But anyway, when that state is identified and it's time to suppress alarms, we've defined kind of a rule set for defining the alarms that need to be suppressed when that state becomes active. So for a compressor, first we define the different states of potential operation, whether it's running or starting or stopping or whatever. Our concern in this case is the tripped state. So then we turn our attention to how do we know when the compressor has tripped unexpectedly. There are certain process variables and measurements and things we could look at. We could look at the interlock trip status, perhaps, look at the status of the motor that's driving it or the drive, and the speed and whether a low speed alarm has been created. So we want to look for what are the process conditions that we can bank on to know when the compressor is tripped. And then once we're able to define that, then we want to think about what alarms should be suppressed when we detect that the compressor is tripped. So this case could be low flow alarms, bearing temperatures, etc., the stuff that you expect to be there because the trip has occurred. And ideally, we want to replace those with a common alarm instead, or the alarms that are still valid and meaningful and useful to the operator. So there may be some, particularly if it's related to the first out of what actually happened, what actually triggered the trip, that would be useful for the operator to know. And oftentimes you can kind of get a early feeling of what alarms should be potentially included in the suppression group by thinking about the cause and effects that go with the scenario. So if it's a predefined trip state where an interlock activates, what are the devices that get moved based on that, and what alarms would be created as a result of that. So you can oftentimes identify during even a PHA when you're going to have a potential alarm flood scenario occurring in the future because of a trip that's going to occur, and the action that it's going to take is going to cause a lot of alarms. So you can very early on in the process hazard analysis not only identify the potential for an alarm flood to occur during operation, but also what are alarms that are very likely to be generated in that case. So now let's look at how we would evaluate and implement and define that within the SILAlarm alarm rationalization tool. So we've done alarm rationalization already, and then three main steps within the tool. First, we need to kind of define the alarm flood suppression group. Then we need to define the trigger conditions, so for the creation of the state detection algorithm. And then the last step is to identify what alarm should be suppressed when the flood suppression scheme activates. So the first step is to identify what the purpose of the suppression group is for. And in this case, if we're working with the DeltaV system, we pick which of the pre-configured control modules for alarm flood suppression we'll use, either 16 or 32 alarms it can work with. And then we want to define the trigger conditions for the state detection algorithm. So what's the process variables that we should look at to determine when the compressor is tripped? So we're looking at analog values, we could be looking at discrete statuses, and we're defining it in two different ways, not just the English description of what's happening, but also the actual logical description that will go into the control system, in this case go into DeltaV, so that it can actually determine logically whether something is happening. But these condition descriptions are what actually would be then shown in the HMI to the operator. So they would see those as the conditions that are defined to initiate the suppression, and they would have a status to know which of those conditions has been satisfied. So when it comes to implementing state detection, here are some best practices or tips coming from that technical report number 4 from ISA 18.2 committee. So we would never want to rely on just one single point or one single measurement, because if it has problems, say it's an analog point that's cycling around the set point to kick off the suppression, then we would have not a chattering alarm, but we would have a chattering suppression scenario, which would be really bad. So we want to make sure that there's high reliability in the suppression scheme to kick off. So we would want to look at least two different independent pieces of information to determine that the suppression needs to be kicked off. And we want to make sure that those pieces of information, those sensors, those measurements are not related so that they could fail by common cause. If it's an analog point, as I mentioned, we may need to implement deadband. But you also want to make sure that, again, that you're looking at more than one sensor to create confidence and ruggedness and reliability in the algorithm. And again, it would also need to handle how you deal with bad sensor values, so bad PVs. You wouldn't want the suppression scheme to be kicked off because one of the process measurements went into a PV bad condition. So you need to make sure that you're addressing and thinking about all those when you come up with the state detection, which is really the hardest part of this activity. Once that's done, then you're ready to select which alarm should be suppressed. In SILAlarm, we can filter to give us the list of alarms that are relevant to sort through, the alarms from that particular piece of equipment, and then we identify which ones need to be suppressed. And if we look in detail at the information that's there, we have the priority of the alarm, we have its classification, and we have information as to whether it's being claimed as a safeguard or an IPL. And that all gets documented and discussed during rationalization. So that's another reason why I believe rationalization should be performed first, because then you're going to look at these alarms and you want to make sure that it's okay to suppress them. So if you look at an alarm and it's the highest priority, or it's classified as a safety critical or a safety related alarm, or you're taking it as an independent protection layer, then you maybe need to think a little further about whether it should be suppressed or not. Perhaps it shouldn't be. And just because a piece of equipment is tripped doesn't mean that blanket statement all of the alarms can be suppressed. There may still be some undesirable situations or potential hazards that exist that you would need the alarms to be there for. So many alarms can be suppressed, but you should go through every single one by one to make sure that it is okay and it is acceptable to suppress them. Now, one of the downsides to doing this automatic suppression is you have no visibility as to whether alarms are actually going off when they should be. So some people take the algorithm a step further and say, I want to have notification if one of the alarms that I expected to go off that's being suppressed didn't activate the way it was supposed to, or the trip did not actually proceed the way it was supposed to. So some kind of notification to indicate that. So then when we put it all together and look at the summary of the capture of the information, this is what we would have in SILAlarm. And we then export that from SILAlarm to a text file, which can be directly imported into DeltaV, and will automatically create the control logic to run in the controller. That comes with faceplates and such that allow the operator to control whether the suppression is active, to view the status of the suppression, whether it's kicked on or not, and if it is, which are the conditions that caused it to go active, and if it was a voting scheme, which are the first outs, as well as which alarms have actually been suppressed at that point. And you can see one of the things it does is it automatically puts all those alarms into a suppressed alarm list. That is a mandatory requirement if you're doing design suppression, that if alarms are being suppressed, we don't want to hide that information. We want to make it available for the operator to see if they need to or they want to. So suppressing removes the alarms from the standard alarm summary display, so the active alarm summary display, and puts them on a different display, in this case the suppressed alarm list. So the operator can always go to find out what's going on, to see the list of alarms that have been suppressed, and to manually unsuppress them or one if need be. Now, there are things that you can do with the HMI design to help the operator respond or help the operator deal with alarm floods. Certainly the way alarms are listed or ordered on the alarm summary display can make a huge difference. Typically, alarms are displayed either in priority order, highest alarm at the top, or chronological order. Now, in some research that was done by the Center for Operator Performance, they found that if you structure your alarm summary display where the highest priority alarms are always displayed at the top, that actually allows the operator to deal with more than potentially 10 alarms per 10 minutes. It was the most effective way, or the operators responded most effectively in that kind of a design. They could actually deal with and process almost 20 to 30 alarms per 10 minutes if they were experienced operators. So experienced operator in combination with a smart design of your alarm list where you've got just the highest priorities displayed at the top helps the operator in dealing with processing the alarms that occurred during a flood. And one of the thinking that goes into this, one of the thoughts is that the design with highest priority alarms at the top means delayed responses to the lower priority alarms. Well, if you've done rationalization, then that's actually what you would want to do. If there's an active high priority alarm that needs the operator's attention, that should always be more important to respond to than a low priority, because the low priority should have a much less significant consequence. Another thing you can do within the design of the HMI is to aggregate or roll up the alarm status for each process area or each unit, so that from a situation awareness point of view, the operator can understand what are the areas that are having the problems, where is the upset, where is the flood occurring, so they know which areas to focus on and which ones they don't have to worry about because they're working fine. Now let's talk about how to implement alarm flood suppression in some other control systems. So here's an example of a Siemens PCS 7 system where the alarms are generated in the automation system, the controller. And the way it works is you define rules within your engineering system to hide alarms depending upon state. And I'll show you how to define that logic. But essentially what occurs is when the alarms are generated, they're all put into the archive, but this filter or this hiding matrix that we define in the engineering system controls which alarms actually get through and get presented to the operator. And here's a blow up of how that works, a little bit more detail. In the automation station, we've got our control logic, our CFCs, to indicate whether the compressor has tripped. We have compressor states that get driven into a state rep chart, and that is what interfaces with our hiding matrix. So in the engineering system, we define for each state, and a state would be a column, whether an individual alarm, and that's a row in this view, should be suppressed or not. So each alarm we're indicating suppressed or not depending upon the state. And here's a bigger blow up to see what that actually looks like. Each row is a different alarm. Each column here is a different state as detected. And then the checkbox indicates that that particular alarm, that particular row should be suppressed when it's in that state. And then those alarms don't appear on the active alarm summary. They go to the suppressed alarm list or the hidden list in PCS 7. Now looking at a Yokogawa system and CAMs, you can define alarm groups in a filter that can be manually activated. So the operator can say, I want to switch to this filter that's predefined to filter out certain alarms, either individual alarms or alarms that are of a certain priority. They take that a step further with what they call load shedding, which is actually invoking automatically a filter. So you could define that if the system detects more than 10 alarms in 10 minutes or some other metric, that you automatically filter so that the operator only sees the highest priority alarms. So similar to what we had just talked about. And that, if you've done a thorough alarm rationalization, that's a valid approach to help the operator deal with the situation, because focusing on the higher priority alarms should be what is best in the upset situation. If it's a low priority alarm and it's not responded to, either the consequence would be relatively minor, or you're going to end up with a higher escalation alarm, and eventually you get to the higher priority where the operator sees it. So sometimes this type of an algorithm can be useful. In the Yokogawa system, there's also an add-on called Exapilot, which allows you to define and set up the alarm suppression in a way that actually matches up with what we defined in SILAlarm. So it's kind of the same algorithm, the same parameters, the same input goes into that as what we saw in the SILAlarm tool. Looking at the Rockwell PlantPAx system, each alarm in the control system and the logic has a suppression input bit, a programmed suppression. So you can set up logic based on the state that's detected, the compressor trip, that would suppress the individual alarms when that state is detected. And then the information about that, whether the alarm is suppressed or not, is displayed and shown within the HMI displays on symbols and on faceplates, as well as put onto the suppressed alarm list. Now, everything that I've been pretty much talking about to this point and showing you is assuming that we are defining alarm suppression and it's being implemented in the controller. So it runs in the controller alongside the control modules that are generating the alarms. So we'll call that the embedded approach. Now, there is another approach that used to be used more frequently. We'll call that the supervisory approach, where sometimes maybe even a third-party software is connected to the system, and that's where the alarm flood suppression algorithm runs. So what it's doing is reading statuses using OPC from the control system, and then processing that, and then taking the actions from within it, which would mean it needs to write down in the control system using OPC to the alarms to either disable them or suppress them, whatever mechanism is used. So it's actually reading the statuses via OPC and then writing directly into the control system to the alarms. Now, more and more with the reality of the threat of cybersecurity and risk and vulnerability from that kind of connectivity, this supervisory solution is becoming less and less ideal. So that's one of the reasons why we recommend and we tend to favor the embedded approach. Now, there are pros and cons to both approaches, and there are certainly applications where one would certainly be better than the other, but generally speaking, we prefer the embedded approach. And kind of summarizing or getting to some of the main impacts, again, of having alarm floods, if we were taking credit for alarms from a safety point of view, from a functional safety point of view, if we are having alarm floods, then we have to, or we should really assume that it's not going to be likely that the operator will be able to respond reliably to prevent the consequence from occurring. So if you're having alarm floods, you should not take credit for alarms for risk reduction. You should either redesign your risk reduction schemes or get rid of the alarm floods so that then that alarm becomes a reliable entity. And one thing that's sometimes challenging to understand is when we're analyzing these layers of protection, if it's a hardware, mechanical, electronic layer, we can relatively easily calculate the probability of failure on demand if we know the underlying failure mechanisms. And we can think that we can do that for an operator response. But the problem is operators are very different depending upon who they are and what's been going on and the human factors element, the human side of it. So it's really difficult to do a accurate probability of failure on demand calculation for an operator unless you're considering the fact that their reliability is going to change potentially tremendously if they are getting floods of alarms. So that's why we recommend not taking credit for alarms if you have a prevalence of alarm floods. So now getting to the end here and to the summary of the presentation, certainly we've talked about how alarm floods can cause significant problems, stress on the operators, lead to mistakes, lead to incidents, unplanned downtime, damage to equipment. We also saw that addressing alarm floods is typically a different problem than addressing steady state alarm overload, which rationalization typically can address. Rationalization can help reduce alarm floods, but it may not be significant unto itself to totally eliminate them or get them to the point where you want them to be. We saw how HMI design and alarm summary displays in particular can be set up to kind of optimize the operator's response and make it as efficient as possible for them to be able to deal with the maximum number of alarms. We also talked about how to create an alarm flood suppression mechanism then that would automatically detect the event occurring. We defined detection logic, and then would suppress a group of alarms that you've predefined that should be suppressed because they're not meaningful when that event occurs. And we saw how that's presented to the operator and what that looks like. And we also talked about how the implementation architecture, whether you're implementing the alarms in the controller itself or in a supervisory PC, does matter. And last but not least, if you are taking alarms, if you're taking credit for alarms for risk reduction, and you have alarm floods, you should probably rethink that strategy and either redesign your layers of protection or address the alarm system performance problems so that you can assure that the operator response will be reliable. So now we're getting to the end of the presentation here. So if you've enjoyed this and this is your first webinar and you want to learn more, I suggest going to our website. We have a whole bevy, a library of previously recorded webinars on other alarm management topics, as well as functional safety, cybersecurity, and other topics as well. So definitely encourage you to check those out. Also, this is a list of some of the upcoming training classes, as well as new classes that will be available online. And in particular, I'm excited for us to now be able to offer the ALM 102, Fundamentals of Alarm Management for the Practitioner class, for which folks will be able to take the Alarm Management Practitioner Certificate exam to show that they've acquired a certain level of knowledge and expertise. So now that program is fully available and ready to go live. So I'm very excited about that. So now let's let's draw to a close and see whether there are any questions that we can answer here. And we have a question, is there a guide or template available to write a typical alarm philosophy? Actually, Exida has a template that we use when we help people create alarm philosophies. It's got predefined text and such for every section that's needed. And there's actually a pretty extensive section on advanced alarming containing a lot of best practices coming from AMUA, coming from that technical report number 4, and other industry recommendations. Good question. Looks like that might be the last of our questions. So on that note, I'm going to say goodbye and thank you very much for attending. And I hope you'll be back to attend a future webinar.